Joe really requires no introduction, but so I will not even try because Joe will do a great job. But anyway, let's give a warm welcome to Joe.
Thank you everyone. I hope you've all had a nice lunch. I hope you're feeling nice and chill. I'm going to talk to you today about this thing here. This is a wearable live captioning display that is inside a mask. But before I dive into the tech, let me first introduce myself. My name is Joe Franchetti and I am a developer advocate at Ably. Ably is an edge messaging platform which helps developers like yourselves to build live and collaborative real-time experiences into your apps. We've got an ever-evolving suite of SDKs and APIs that give you the freedom and flexibility to power collaborative experiences like chat, definitely chat, and asset tracking, multiplayer games, even real-time experiences like live captions. And I'm primarily a web developer, but I also dabble in IoT. I like to put LEDs into things because I like to be sparkly. I put LEDs into my wedding dress. I made a Christmas jumper that shows a different emoji depending on which Christmas music is playing. And I have to admit to a personal desire to want to see more things like this wearable live captions on the market. And the reason for that is my mother. So this is my mum, Mama Franchetti. And she's a smiley, sociable, quick-witted woman who likes to have a good natter with her mates. But she's been steadily losing her hearing over the last few years. She went to too many rock concerts when she was younger and didn't wear earplugs. Just wear earplugs, folks. But losing her hearing has been an incredibly isolating experience for her, as I'm sure it is for many other people. She relies really heavily on lip reading and clear enunciation. And you know what makes lip reading and clear enunciation really difficult? Wearing a mask. So if she was struggling to keep up with conversation before, once the pandemic hit, it made it almost impossible for her. She couldn't socialize safely with her friends, she couldn't understand people who were talking to her in shops, and people have a tendency to become quite rude when you ask them to repeat themselves, and they'd brush her off. And she couldn't catch what was being said, and she would get very self-conscious about it. She didn't want to ask them to repeat themselves multiple times, and she was trying to style out what they wanted. So I had a couple of asks from you all during this talk, and the first one is this: if somebody asks you to repeat yourself, don't respond with never mind or don't worry. It's incredibly frustrating for someone who is hard of hearing because they're really only getting half of the conversation. And as we traverse that hearing loss, one thing has really struck me, and that's as developers, as a group, we're just really not doing the best job that we could do with basic technology. My mom has a cochlear implant, which is super cool. It's a little device which is inserted basically into her head. She has a processor which is sort of attached to her brain. Like, my mum is a cyborg. Kind of cool. And so it has a little processor on it and a battery that clips over her ear, and it can stream sound directly from her phone or from her television directly into her head. So she doesn't need to use headphones anymore, which is kind of cool. But the app that comes with the cochlear implant, like this thing that's inserted into her head, only works on iPhone. So she couldn't use her Android phone anymore. She had to swap to a phone that she didn't know. And not only that, iOS released an update about a year or so ago that caused everyone with this particular brand of cochlear implant to hear screaming in their ear for about 2 days before they released an update that fixed it. And it's really not good enough. We should be thinking about these things when we're building, we should be testing assistive technologies, and we can all do better than this. Assistive technologies, just, it's not the most sexy thing to work on, so they don't get the attention that the more glamorous projects get. But goodness, we're better than streaming screaming into hundreds of people's ears. And my second ask of my talk is this. Oh. Where is my cursor? Apologies, everyone. There we go. Let's put some effort and accessibility in. Let's put some effort, rather, and development time into building accessible technology and assistive technology, and let's help our fellow humans. So, story time is almost over, I promise, but I was really worried for my mum during lockdown. Like, she was getting increasingly isolated. The assistive technologies that are available to her, they all run on her phone, so if she's conversing with somebody, she has to be looking down at her phone to get the captions, and people think that she's not concentrating on what they're saying, so they disengage and start talking to somebody else. And we're all developers, we like to fix problems, so I thought there should be something that I can build here that can make this better for her. And inspiration struck me in the weirdest of places. So if you're visiting London or you live in London, you may have been to this place here. This is Cyberdog in Camden. It's well worth a visit if you haven't been. It sells basically rave clothing. So anything you can imagine with LEDs, bright lights on it, you can buy it there. And they were selling the thing that you've actually seen Dylan already wear. So this really cool mask with LEDs in it. And the mask had a high enough resolution that it could run all these fun animations. And I bought one immediately thinking, I can put text on here, this is going to be brilliant. I can signal what I'm saying to my mother so she can look at my face while I'm speaking. But the display in the mask came with its own built-in processor, with its own app that is very locked down, so you can't really stream to it. You can only set particular images or set a particular sentence. I tried to reverse engineer the app. It was written in Chinese. We tried sniffing the Bluetooth packets to work out what it was sending, and we couldn't get it updating fast enough in real time. So, not wanting to be beaten, I thought, why not make it myself? So if we break down the mask into its component pieces, then what we really need is some kind of flexible LED display that is wearable. The LEDs that are used in this are called addressable LEDs, which means that each of them has a number assigned to it so that we can send a particular piece of data to it, so a color and on or off. We need a way to then control that display, so to send the data, some sort of small processor board which is going to be able to be secreted somewhere on the body. And we need all of this to be small enough to fit in a mask. We need some way to then power it, and we need some way to send data to it from my mouth to the mask. So the wearable display part, I'd done a lot of work with LEDs before, as I mentioned. It's an array of 28 by 8 neopixels. These are very tiny little LEDs, so you can see a slightly larger example of them here. And do feel free to come up and have a play with these later. So this is a larger version that I bought off AliExpress, obviously way too big to fit in a mask. I needed to buy much smaller strips of LEDs, and I've soldered them together inside of this mask here. And the great thing about buying the strips is it means that there's gaps between, so you can actually breathe through it nice and easily. And it's powered by a very small microprocessor. So the microprocessor actually fits inside of this box here. It's tiny. It can be powered by a USB battery, so something like this size here, which is obviously very easy to carry around. You could fit it in your pocket or potentially even fit it in the mask. And the board that I'm using, the microprocessor, has Wi-Fi on the board, so you can see the antenna just here. Now, I could have got a tiny little microphone and attached that onto the board, but honestly, doing audio streaming on a processor this small is perhaps a little bit too much for such a tiny little board. But the board does have Wi-Fi, as I mentioned, and these days everybody carries one of these devices around with them, which has its own microphone built in. So I could listen to the audio with my phone and take the audio processing, do it all on the phone rather than do it on the board, and then send the text from that audio processing to the board to display. So I built a little web app. And web APIs make it super easy to use the phone's microphone. I'm sure a lot of you have done it all already. And then I translated the audio that was picked up by the microphone into text. using Azure's cognitive services. If you've not used cognitive services before, it's a suite of APIs that allow developers to add AI capabilities to their apps really easily. And one of these capabilities is speech to text. Oh no, we lost an I. The web app is a nice simple Node app that uses a few different packages. So as I mentioned, we're using the Azure Cognitive Services Speech SDK. Then we've made a driver for the LED array, and then we're going to need a transport protocol in order to send data from the app on the phone to this little microprocessor here. And the app itself has some really basic UI. Here's what it looks like. So we have a button to turn on the mic to start listening. We have a box which is going to show the returned text from cognitive services, which is actually what you're seeing here, along with a visual representation of the LED array for debugging. And also I've added some settings so we can change the color of the text on the mask, and we could change the speed that the text is scrolling. So let's start by hooking up that Start Listening button and sending data to Azure Cognitive Services. So I wrapped the Cognitive Services Speech SDK with this code here. I don't know if you can see it or if that's a bit small for you, sorry. But under the hood, what this is doing is it's using the Speech API to do get user media, which is just how we get data from the microphone on your phone. And when the user clicks the Start Listening button in the app, this function is called, which uses stream speech from browser, which you can see there. So then Azure is going to use our from default microphone input along with an authorization token so that we can authorize with Azure, and it's going to initialize this thing called a speech recognizer. And this is what is going to perform the speech recognition on the data that we're getting from the microphone. And it's going to return an object, which is just the text of what has been said. And then in the main app, I wrapped the cognitive speech services with a class to provide it an API key. And then I register a callback on text recognized, which will subsequently call the LED driver that I wrote, which I'm going to talk about in a little bit. And it'll send it the text along with a color that I want to send and a scroll speed. But before I talk about the LED driver, let's talk about actually communicating with the hardware itself. How do we get this transcription, which is now on my phone, to this device here? We need some kind of messaging protocol. And usually for IoT type projects, you'll want to use something called MQTT, which is a lightweight publish and subscribe protocol which is designed specifically for IoT. It's optimized for high latency, for unreliable networks, and it's perfect for this kind of project where we might be on a 3G, we might be on a dodgy connection, we've got a very low power device, we're running on a USB battery. And in order to use MQTT, you're going to need some kind of MQTT broker, and this is the service that is required to dispatch the messages from the sender to the rightful recipient, so in this case, the client, the mask. This project uses the Ably MQTT broker, which comes for free if you're using the Ably SDKs. And what we're doing is the web app is going to send messages over WebSockets, and they will automatically be sent out over MQTT as well. So we can connect not only with our IoT devices, but we can connect with other phones as well, other devices which understand WebSockets. And as I mentioned, the microprocessor is really small, so it has very limited processing power. It has very limited memory, it has very limited actual power, which means that the code that it runs needs to be as efficient as possible. So we want to avoid doing things like parsing text or other similarly memory-intensive tasks. Parsing and splitting strings is quite costly and it involves large buffers, and we just don't have the memory on the board. If we use up the memory on the board parsing the messages, then the amount of memory available to us to actually buffer the messages, because when you're talking, obviously it's a long stream of text and we might need to buffer quite a lot of it in order to scroll it past. So the more memory we use up, If we don't optimize the performance, the less we will have available for buffering. So to solve this problem, I used a binary message format which talks to the hardware. So the browser creates a specifically encoded message and sends text strings to the device. So this is an example command. It's in JSON. We should all recognize this. Instead of using JSON, we're going to use a binary format to encode our data, where the content and the order of the bytes is all relevant to the hardware. So for example, in order to scroll text across the display, we might want to send a message that looks like this. So we have a line of text, we have set a scroll speed, we've set a color, and we've told it what mode we want it to be in. So we told it we wanted to scroll. Rather than sending it as JSON, we're going to encode it and pack it down. And these packed down messages are sent as raw bytes, and then we can use control codes from the ASCII standard to provide some header information in the messages. And because the message is just a raw byte stream, we don't need to parse all the messages on the hardware. It can just loop over each byte and run different processes depending on which byte is being looped over at the time. And the cool thing is that this takes all the complexity out of parsing text away from the microprocessor and puts it in the JavaScript code where really it should be, where it's much easier to debug and test. So if we have a look at this table here, the byte at offset number 8 is going to represent a single character. So that's that one here that you can see in orange. But the parser on the hardware is looking out for the STX and the ETX, so it's looking for the start and the end. This means that any number of ASCII characters can be added to that space in between the start and the end to form full sentences. So that's how we can send messages. So next, let's look at actually hooking up the speech recognition. So earlier on, we registered a callback to onTextRecognized, and that called the matrix driver. What we didn't look at is how we make a connection between the browser and the LED driver using Ably's MQTT broker. So there's a few things going on in this code sample here. First of all, we're making an instance of the Ably JavaScript SDK. Then we're making an instance of the remote matrix LED driver, and that's part of the LED driver package. It's going to take a display config, which tells us how big the display is. So in this case, it's 28 by 8. This one is, I think, 36 by 8. It means we can have any size of display that we want. And it needs a device adapter, which tells us about the encoding protocol that we just described. So let's talk about the device adapter now. It's going to implement the binary protocol that I just described, and it requires some kind of transport. So here we've got a wrapper for the Ably JS SDK, which is how the data is going to be sent. When the data is sent over WebSockets by the Ably JavaScript SDK, it's also sent over MQTT automatically, as I mentioned before, which is super cool. And this feels like a lot of information I've just sort of vomited onto you, I apologize. But what this means is that when we call the functions available on the Matrix SDK driver, it now knows how to convert pixel locations to absolute numbers, and it knows how to encode those numbers into a wire format using the device adapter. So it's able to swap between width and height of 8 to what addresses the LED in this array. And it knows how to transmit the data from the web app to the device over Ably MQTT. So if we were to visualize the whole process, it looks like this. So now we have a way to compact those messages down. Let's take a look at the display driver and actually see it reading those messages. So the LED driver was written for a previous project, so I made a t-shirt where you could draw in LEDs, kind of like a really low-res version of MS Paint. And then I made a jumper that showed different emojis in LEDs depending on what Christmas song was playing. And so this driver can do a whole load of different things. I can set a single pixel, which I use for the Paint app, with an optional color, either in hex or RGB. I can also set single pixels where the Y coordinate is optional, and it'll default to 0, so if I've got a single strip array. I can set the entire display at once using some nice visual coordinates. So if I want to draw a picture, for example, an emoji, to a square display, I can do. And I can even send entire images to the display as long as the image is a low enough resolution that 1 pixel equals 1 LED. But for this mask, I needed to be able to not only show text, but show scrolling text, and also have a optional color change and an optional speed setting. And I'm sure you can imagine, scrolling text is a lot more involved than setting a single pixel on an LED, so let's take a look at how I did it. The first thing that I did was I designed a pixel font, and this has a whole load of alphanumeric characters in it, which I needed to then convert into binary values. I sort of took a guesstimate at the ones that will be most likely to be used from speech, so obviously this doesn't cover every single character possible. And I then converted each of the letters into an array of pixels. So let's take a look at, for example, the letter N. So hopefully you can see that there, represented visually. This is a letter N, and if we give each of the pixels in this array a binary value, so 0 for off and 1 for on, our array is going to look like this, which if we make it look more like text, it looks like this, and if we put it in one long line, it looks like this. So this is just the letter N, which has been encoded into a binary array. And instead of encoding the entire alphabet by hand, which would have taken a really long time, luckily there is a library that can do that for us. So GIMP is an NPM package. It's really great. It was able to encode the entire little font set that I made from a PNG. So I've taken a bit of design liberty here. If you imagine this whole font in one long line rather than wrapped around, you may notice that the characters aren't all the same width. And personally, I think it looks nicer. A monospace font, I think, would be more difficult to read in a scrolling display that is so small. But this means that not only do I need to encode each letter, but I also need an array of indexes of where each letter starts and ends in that array. So I have now 2 byte arrays, one which is the whole alphabet and one which is the indexes of where the letters start. But these 2 byte arrays are still so small, they can be stored on the little device with no problem. And then with that embedded, it's possible to write some microprocessor code to show those letters on the display. And this is great because it means instead of computing all the individual pixel positions in the browser app and then sending them one by one, the microcontroller can handle that calculation itself. So, cool, now we have a font. We need to work out a way to display it on the array, which, as always with hardware, if any of you have built any hardware projects, nothing is ever as easy as you would like it to be. And I discovered in making this project and making other projects, that LED displays can be wired up in a myriad of different ways. So the first one that I bought, this one, you can actually, if you come and have a look at it later, you can see how it's wired up on the back. It's up and down and up and down and up and down all the way across the array. When I wired this one up, I did it horizontally rather than vertically. And there are some that you can buy that start on the left and end on the right, like you might read. Each of the LEDs in this array are addressable, so they each have a number associated with them. So we need to work out how it was wired up and therefore which way they are numbered so that we can work out which pixels we need to illuminate. Not only that, some displays, you can see on the back here, have connectors at either end. So we don't necessarily know which end the data is coming in and which end the data is going out. So it meant that I had to consider all these different physical constraints and how the wires are, I called it snaking, so we have different snake modes for wires. when I'm calculating the correct pixel ID so I can work out which ones to illuminate. But once I was able to do that, it's, are we adding, are we subtracting, depending on the direction that we're going? Are we going horizontally, are we going vertically? I was then able to convert between a coordinate that is being sent for, this one's 0, 1, 0, 2, 0, 3, and what is going to be illuminated on the hardware. So I can then configure the board to tell it what kind of display it's using, which means that we can connect this little microprocessor up to any display and give it any configuration, and it'll be able to display text on it. The microprocessor has a single configuration file, and it looks a little bit like this. So we've got a few different settings that we need to do here. So first of all, we're telling it which I/O pin the data is being sent out on. In this case, it's pin number 4. I'll open up the box later, and you can come and have a look at the board and the pins if you'd like to. Then we have the display width, which in this example is 32, the display height, and then whether the connector is going in the top left or the bottom right, and what type of snake mode it is. So in this case, snaking vertically or snaking horizontally. And then the final gotcha was pixel type. So there are different types of pixel LEDs that you can buy. Some take 3 values for a color, some take 4. RGB LEDs take 3, RGBW take 4. You will need to double check which ones that you have bought when you are using them with an Arduino, because if you send 3 values to one that is expecting 4, it's not going to light up in the way that you expect. So when any message arrives at our device, it runs through this initial passing block here, which will interpret the message that the LED driver has sent. It's going to check the first byte for the control code, and then it's going to check the second byte for the control mode. So am I sending just a single pixel? Am I sending some text? Am I sending an entire image? Is it scrolling text? And then the Arduino device driver needs to be updated to send the messages using the correct control mode, and to say whether it's scrolling, how fast it's scrolling, that kind of thing. The microprocessor software is able to set pixels on a display of any size, as I mentioned, and we've already stored the fonts. So the missing piece is to write message handlers to actually process those incoming binary messages. And what they're going to do is look up the font data for each character in the message, and then push the appropriate illuminated pixels to the display. So when a message is received, the code is going to loop through each byte loop through each text character, and look up that character in the embedded font. So you sent an N, we're going to look up the N, where is that, and what does it look like as our binary array. Because the font data includes the width, the code will then iterate over the correct number of characters, and it can calculate the location that it needs to start drawing at on the LED display. So if we call that position the X position, each time a character is drawn on the display, we need to move along. Not only do we need to look up the index, we need to look up the width of the character, and then we need to move along that many pixels before we start drawing the next character. And as the code loops, all of the XY coordinates are returned from the font, and we are able to draw the letter, look up the X position, add 1 extra space so that we have a space between each character, and then draw the next character, and so on. So that is going to write text to the display, which is great, but we also want to scroll that text. And luckily we've got this X position already, so we can scroll the text by always starting the X position at the right-hand edge of the display, and then increasing it over a certain amount of time, and drawing the new pixels as we move through the letters. We write a loop that will decrement the X position, so if it starts at 32, it'll go down until it reaches 0, and we have scrolling text. And this is super awesome. Every time we run that loop, we can set some kind of delay, which gives us the scrolling speed, and it's a really nice way to scroll the text across the screen. So If the message code indicates scrolling text, we start a while loop that updates the scrolling position, and it starts looping until the subset of the total data into the string is all scrolled off screen. So we make sure that we don't like stop a word halfway off the screen. We want everything to disappear. And every time this animation is played, it pauses the execution of the code, and this loop stops the control being returned to the main Arduino loop, which would trigger receiving more MQTT messages, which is super cool because it means that we can use MQTT as a buffer without using up the memory on the device. So until it's finished scrolling, it won't receive any subsequent messages, then it'll be able to scroll those. That was a super quick introduction to what is happening here in the mask. That was basically it. The mask was then built, and here is the finished result. This is me showing it to my very bemused mother, who was not 100% certain that this was the solution that she needed, but she did enjoy that I tried. And there is a tiny bit more for me to tell you. So there's a few parts of the app that I've not spoken about because we would be here all day. One of which is if you don't have an LED display, don't worry about it. Inside of the app, there is a demo display which visualizes all of the LEDs as divs, so you can see what it would look like. One of the joys of using Ably to build this thing in the web app is because we're using the JavaScript SDK, everything is sent out over WebSockets, so if your user doesn't have the mask, they can of course still use their phone and it'll still work. And in fact, you can share your live captions with potentially millions of people if you wanted to. You could have individually held live captions for an event like this, for example. And if you visit livecaption.ably.dev, you can actually see the demo and have a go of it yourself. The entire project is available to you on GitHub, so if you would like to build your own, or if you're doing anything with IoT or MQTT, it's all open source. I would really love you to take it and make it your own. Make something new and brilliant. If you have any luck backwards engineering that mask that Dylan's got, let me know, get it running on that. I would love to see it. If you want to build any other IoT projects, the Ably Labs repository has a load of demos in there as well, so if you want to build a chat app or a multiplayer game or a quiz, have a look in there. There's a whole load of open source demos in there for you. And if you do try out any of them, do let me know about it. My handle is thisisjoefrank, or you can join us on the Ably Discord, which we've just opened, where you can chat with me in real time. And I'm always happy to help with any of your real-time projects, so do give me a shout. And if you enjoyed this talk, please give me a tweet at Ably Realtime so that my boss knows that I'm working. And thank you everybody for listening.